Here we are again for ChemPhysChem's second virtual symposium. Thank you very much for joining us. This time, our invited speakers will be sharing and discussing some of their work in the field of supramolecular chemistry. I'm Kira Welter, one of the editors of ChemPhysChem, and I'm very pleased to be able to bring this event to you today on behalf of our editorial team and Chemistry Europe. You've probably seen that we have a great lineup of speakers. With us today are Natalie Busschaert from Tulane University, Carson Bruns from the University of Colorado, and Steve Goldup from the University of Southampton. After their talks, the three speakers will be replying to questions from the audience. So please take part in the discussion and send us your questions through the chat. It would be great if you could tag them with the speakers' names so that we can identify them more easily. My colleague Ruben Rack, the editor-in-chief of ChemBiochem, is also supporting us today. So if you have any general questions or comments, please send them as well, and the two of us will try to reply to them. We're really happy to have Nobel laureate Fraser Stoddart as moderator of this event. Fraser is the 2018-2019 Chemistry Europe Fellow. This fellowship is the highest recognition given by Chemistry Europe, and he's also on the editorial boards of several of our sister journals, including Chemistry European Journal and our younger sister journal, ChemPhysChem. So Fraser has been a great support to Chemistry Europe and its publications and to science communication in general for many years, and I'm really, really happy that he has agreed to support us again today. He will guide us through this event, introducing the speakers and moderating the Q&A sessions. So I think the best thing I can do now is hand over to him so that we can get started. Fraser, thank you very much for being with us.
Well, thank you very much, Kira. All right, and people can see me and hear me?
Yes.
Good. Well, thank you very much, Kira, and your colleagues for organizing this symposium. Without any more ado, I will start off by introducing our first speaker. This is Natalie Busschaert from Tulane University in New Orleans, and putting it in simple language, from NO in Little LA. What can I tell you about Nathalie, whom I've never met actually face to face, but might have done, believe it or not, on 11th of November 2016. More on that in a little while. Nathalie was born and raised in a small country called Belgium, which is surrounded by France, Luxembourg, Germany, the Netherlands, and the English Channel. Her hometown of Beveren, close to Antwerp, is within a stone's throw of the Dutch border. And she describes her upbringing there as being a bizarre mix of suburbia, agriculture, and a big cluster of petrochemical companies. And on a clear day from her bedroom window, she could see the flames coming out of the towers from the distillation towers of the industry. So it's perhaps of little surprise to us that she was drawn to chemistry. She did her bachelor's and master's degrees in chemistry at the Catholic University of Louvain. And it was in her final year that she, as an Erasmus student, took herself to Southampton. I just want to put in a note about Erasmus. This is a European funded student exchange program that Brexit is designed by some of the less well-equipped politicians on this side of the English Channel to kill if they possibly can, at least as far as the UK is concerned. All shame to them. Anyway, back to science. She took her time in Southampton to good advantage during a semester with Phil Gale in 2010, and she liked it so much that she continued to spend her next 5 years studying for her PhD with Phil in the area of ion transport, and particularly looking at chloride transporters across membranes. It was obviously an extremely productive time for Nathalie. She netted no less than 25 papers during that time as a co-author with Phil. Nathalie then went to the University of Oxford to join the group of Andrew Hamilton, who was then not only associated with the chemistry department, but was the vice chancellor of the university. only to find that at the beginning of 2016, he was moving to New York University to become its president. And so Nathalie was, in fact, the only student that moved across the pond to join Andrew at New York University. So now back to this date of 11th of November, 2016. This was a day when chemistry welcomed Andy Hamilton to their midst at NYU, but even though I was a speaker and scheduled to be there, Nathalie couldn't be there for the very simple reason that she was on a job interview to Tulane University. And so the fact that we didn't meet ends up having a good ending to it. This is where she got her academic position. Congratulations, Nathalie. So now I will leave you, Nathalie, to take over and tell us about your alternative applications of synthetic transmembrane transporters, from optimizing optical centers to drug delivery. Over to you, Nathalie.
All right, thank you, Fraser, for the kind introduction. So I will now share my PowerPoint. So my talk is called Alternative Applications of Synthetic Transmembrane Transporters. So obviously that means I should start with an introduction of what's the current most common use of synthetic transmembrane transporters. So most of the study by supramolecular chemists to make transmembrane transporter is guided by the fact that in nature, the lipid bilayer that's surrounding cells is a very good barrier for polar molecules. And then we have transmembrane transporters, usually ion channels, that control the passage of polar molecules and ions. And so it's really driven by trying to mimic these proteins that normally do ion transport across membranes. And the main reason has been that there have been some diseases that are linked to malfunctioning of ion channels, which are called channelopathies. And the most famous of the channelopathies is cystic fibrosis, which is linked to the cystic fibrosis transporting ion channel, which is a chloride transporter. And so the idea is that if we make small molecules that can transport chloride, it could maybe be a therapy for cystic fibrosis. And so most focus has been on trying to develop small molecules that can transport chloride ions. There's been some other natural products that have been of interest, like proteoglycan, that is also shown on the slide, which is also chloride transporter. It's a natural product, and valinomycin, which is a potassium transporter, small molecules. So those have really been the inspiration for developing synthetic transmembrane transporters. And so this is pretty much where most of the field is going. It's chloride transport, cystic fibrosis, anti-cancer, and antibacterial activity. But you can come up with other ions that you might want to transport for other applications. For example, maybe iodide could be linked to thyroid diseases. There's some other inorganic anions that are linked to channelopathies, but those are really rare diseases. A lot less common to be studied is organic anions that you could also transport. That might be useful for mimicking the organic anion transporter proteins, but it could also have implications for drug delivery or drug-drug interactions, which I will talk about later on. Another thing is metal ions, like the potassium bivalinomycin, has antibacterial activity. Also, there's been some channelopathies linked to metal transport. And so these applications are all medical applications, and they're all very useful. But in principle, you could also use synthetic transmembrane transporters without any medical application as such, but based on the fact that if you make liposomes, you have a small compartment that is shielded from the rest of the environment. And then if you use synthetic transporters, you can sort of get a semi-permeable barrier in there, which can have a lot of applications. Sensors could be a possibility, artificial photosynthesis or artificial cells, as well as catalysis. It could all be applications that are not medical related that you can use with synthetic transmembrane transporters. So the first thing that I would like to talk about is using transmembrane transporters to optimize optical sensors, which is done in my lab by my PhD student, Sarah Marshall, and a couple of undergraduate students. So optical sensors are molecules that will give a change in color or a change in fluorescence when it interacts with a particular analyte that you want to sense. So it has a lot of applications, biomedical applications, environmental issues, as well as detecting warfare agents, biological weapons, chemical weapons. Now, to really make these applications work, an ideal sensor should really be selective for its analyte, especially if you have a really competitive media. Water soluble for most applications, you would like it to be water soluble, as well as sensitive, or at least detect the right concentration range for the analyte of interest. And so there's a couple of ways in which supramolecular chemists have tried to develop optical sensors that meet these requirements. So the traditional way is sort of chemosensors or chemodosimeters, where you make a single molecule where the sensing unit and the binding unit are covalently linked into one single molecule, which works very well. But in order to make these kind of molecules and selective and soluble and sensitive, you will need, in general, a lot of synthesis and a lot of optimization, so it can be quite difficult. Now, an alternative approach is the indicator displacement assay. I've just shown a couple of reviews here. There are very large plethora of papers that are available on these kind of things. So with an indicator displacement assay, the signaling unit and the binding unit are not covalently attached, but form a non-covalent complex. And the analyte will then outcompete the signaling unit out of the binding unit, and this gives the optical response. The advantage of this is that it's in principle a little bit quicker to find a selective or a sensitive sensor, because you can more easily try combinations of a binding unit with a signaling unit. But even then, your binding unit is usually what gives the selectivity. So you still need to optimize that one with a lot of synthesis to get there. Now, an approach that's getting a bit more attention recently is sensor arrays. So this is quite different. In this case, you don't have a single molecule that is trying to be very selective for your analyte, but you have multiple non-selective signaling units. And the idea is then that you more look for patterns in this entire array of sensors to identify the analyte and to identify concentrations of analyte using statistical methods. And so obviously the advantage of this is that synthesis should be a lot easier, because you don't need highly selective sensors in this array. But if you would have a very high concentration of a background molecule that also gives an optical change in these sensors, it still doesn't work perfectly, because you'd have a big background of it. And so what we're trying to do in my group is try to just go for an alternative solution to make very selective sensors without going to the highly synthetic routes. And so we call our approach the transporter liposome fluorophore approach, because our approach now has three parts in it. One is a transmembrane transporter, there's a liposome, and there is a fluorophore. Now, the idea behind it is that when you have a non-selective sensor, like fluorescent sensor, you encapsulate it inside a liposome. It is now protected from most of the analytes that could potentially give interference with the sensing. And then we add a transporter to get the analyte to come back in. Now, the advantage of this approach is that neither the fluorophore or the transporter need to be highly selective. We just need a combination of these two that becomes selective. So in the example that is given in the figure on the slide, you will have a fluorophore that is a sensor for X, Y, and Z. So X, Y, Z, and a transporter that might be selective for V, W, and X. And so the only one that is being transported inside the liposome and gives an optical output in the fluorescent sensor is X. And so now we turn this fluorescent sensor from non-selective sensor for X, Y, and Z to now a selective sensor for X. So as a proof of principle, we started with using lucigenin as our fluorophore. So lucigenin is a commercially available fluorophore. It's got a very simple structure. It is usually used for halide sensing because it's quenched by chloride, bromide, and iodide. But it's actually also quenched by a number of carboxylic acids. And so our idea was that if we have this sensor, which is now non-fluorescent, non-selective, can we make it selective for one of these anions? And so our hypothesis was that out of all the anions that are being sensed by lucigenin, the one that is the easiest one to transport should be iodide, which is related with the Hofmeister series. So the Hofmeister series normally ranks anions based on their ability to salt in proteins or salt out proteins, but it's pretty much a measure of the hydration energy or the lipophilicity of the anion. And so out of all the anions that it senses, iodide is the most lipophilic and therefore should be the easiest to go through very lipophilic membrane. There are other ions that are more lipophilic, like perchlorate, but that one's not sensed by lucigenin, so it doesn't matter if that one is transported as well. Now, the fact that this is just Hofmeister based on the lipophilicity of the anion, this means that we should be able to get selective transport of iodide over the other halides, at least, with very simple molecules. So we started with these urea-based transporters. It's a single diphenylurea. We put different substituents in the para position from electron donating and withdrawing to change anion binding ability, as well as to tune the log P a little bit because lipophilicity is very important for anion transport. And so to then determine our system that consists of lucigenin, a liposome, plus one transporter, we wanted to first screen which transporter gives us selective sensing of iodide over the other halides, because the other halides also quench lucigenin. And so for this assay, we encapsulate lucigenin inside ECPC liposomes, and then we add the halide salt to it, and we measure the fluorescence as a function of time. And the typical output is kind of shown in the graph here. So this is fluorescence, change in fluorescence over time. Now, to quantify the sensing ability, we could use two things. We could either go for this F over F0 number at a given time, say at 100 seconds, and we would plot that and determine which one's the best iodide sensor. Or we could use the rate of transport to quantify our sensing ability. And so to get the rate of transport, we would fit the data to an asymptotic fit and then take the first derivative at time 0 to get the initial rate of transport. And the advantage of using the rate of transport is that you get a much larger range of numbers that you can get. They can go in theory from 0 to infinity, which should help with sensitivity and dynamic range of our system. Because you can reach the same F over F0 value at different speeds. So you can differentiate a lot more different concentrations of iodide if we use the rate of transport. And so first thing we wanted to find out is which transporter can give us selective iodide sensing. And so we started with the urea here that has CF3 groups, because CF3 has been very common for anion transport as a substituent that really increases anion transport. Now, the problem is for our system is that this CF3 urea transports everything. So it's chloride, bromide, iodide. It is not selective, so it's not useful in turning lucigenin into a selective sensor for iodide. Similarly, if we have the nitrile substituent, again, chloride, bromide, and iodide, everything is transported, so it's not going to become a selective sensor for iodide. And so the reason for that is because both the nitrile and the CF3 substituents are electron withdrawing, which increases anion binding, but they're also quite lipophilic, which helps with anion transport. So to make it selective for iodide, we have to make the transporters sort of a worse transporter. So one thing we tried, well, we put electron donating groups on there. So anion binding comes worse. But in this case, we killed all transport. Nothing is transported, neither chloride. So that's not very useful either. And so what worked the best is sort of going for the middle ground. So when we have the cell phone, we have something that is electron withdrawing, so it helps with anion binding, but it is very polar. And so because this is now very polar, it is hard for this molecule to transport chloride and bromide, but it does transport iodide. And so in this case, we have selective transport and therefore selective sensing of iodide across all the concentrations of the transporter that we tried. And the only problem with this one is the transport ability is still quite low, which generates relatively large errors, which is not that useful if we're doing analytical applications. And so the one that actually turned out the best one is the easiest molecule out of the entire series. It's just 1,3-diphenylurea. No substituents on there, so it keeps its reasonable anion binding ability. It is not too polar, but it's also not very non-polar. And so this one is our best transporter to get selective transport of iodide, again, across all the board. And because the transport is now a little bit faster, the errors get a little bit smaller. And so we now have identified our system that could be used for selective sensing of iodide in the presence even of other halide anions. So we wanted to check how good is this sensor now if we do this encapsulation into liposomes and add transporters to it. So one of the things we wanted to see is how did this incorporation into what we call our TLF system affect the dynamic range. So just standard lucigenin, not encapsulated in liposome, has a sensitivity, so the lower limit is about 0.75 millimolar of iodide. The dynamic range, if you can see here, this is the percent quenching as a function of iodide. The biggest change is really from this 0.75 to 25 millimolar, and then it starts to flatten out. You can do a Stern Volmer plot of F0 over F, and you get a reasonable linear fit even all the way to 100 millimolar. But the errors get large at that larger concentration because of this flatten out, because it's completely quenched at this point. And you can see quite a big difference if you would only fit the data from 0 to 25 millimolar versus 0 to 100 millimolar. And that's because it is really the most accurate from 0 to 25 millimolar. And the higher ones are not that accurate. Now, when we encapsulate our lucigenin into the liposomes and add this 1,3-diphenyl as a transporter, we did the same thing. So we tried to measure the initial rate of transport at different concentrations of iodine. And again, we get a linear correlation. So that's very good in terms of sensing ability. We want the linear correlation this way. The sensitivity is pretty much the same, so it's about 0.75 millimolar of iodide. So we did not change the sensitivity, which is good. So it's the same as the original fluorophore. In terms of the dynamic range, in this case now, the higher concentration of iodide actually seemed to be a lot more on the same trend as if we would just plot the 0 to 25 millimolar range. So you can see there's a very small difference between those two linear fits. And that is probably to do with the fact that you can achieve the same F0 over F value at different rates of transport. And that's why we can more accurately get the higher concentrations of iodide detected. Now, the next thing we then want to see, well, we increased our selectivity based on our screening. So can we now use our TLF system to determine iodide concentrations in the presence of sodium chloride, which you would not be able to do with lucigenin by itself because it also is quenched by chloride. And so what the graph shows here now is just the iodide calibration. And if we now put on top of there samples of different iodide concentrations in the presence of excess sodium chloride, you see that it's pretty much on the same graph as the iodide concentration, which means that we can determine iodide concentrations in the presence of sodium chloride. And so to just quickly recap this, what we've done now is we've taken this lucigenin, this very non-selective sensor, which is the figure from before, and by encapsulating it in liposomes and adding 1,3-diphenylurea as a transporter, we have turned it into a selective sensing system for iodide. So we've done the experiment with all the anions that we tried originally, and now you can clearly see it went from something where a lot of stuff causes a change to something where only iodide is our sensor. sensed ion. So we are now trying to see if we could use this to optimize selectivity of other systems. So if anybody in the audience has any non-selective sensor that they don't know what to do about, please contact me and we will try to make it a better sensor. Now, the second thing I will very quickly talk about is using transmembrane transporters for drug delivery, which is done in my lab at the moment by Rayana Salam, but also Sarah Marshall's been starting on that. So the idea is here, if a drug needs to be orally bioavailable, or if it needs to cross the blood-brain barrier, it has to go through a membrane at some point. And so if you have a charged molecule, this can become very difficult. But in this case, the problem is pretty much the same as for trying to transport chloride across a membrane. It is trying to transport a polar molecule across a lipophilic membrane. Now, the usual strategy, if you have, say, a carboxylic acid that gives a problem with membrane permeability, is you transfer it into an ester. The ester is membrane permeable and is hydrolyzed once it crosses the membrane. Now, the problem, that's the prodrug approach. The problem with that is that it doesn't always work, the prodrug approach. It has a time delay, and you also have to make sure that both your prodrug, your active molecule, as well as what is cleaved of the ester are all non-toxic molecules. And so that's what's the difficulty with that. And so what we try to see is, can we now use transmembrane transporters as a kind of non-covalent prodrug? So rather than shielding the carboxylic acid as an ester, we are now shielding it by a non-covalent interaction with our transmembrane transporter. So we tried this on a number of carboxylic acid-based drugs. So the structures are all shown here. We did 13 in total. They are pretty much chosen based on the fact that they are cheap enough to buy in bulk to do all our assays with. There's not that much rational design in why we picked these ones. They're just a wide range of relatively cheap drugs. Now, the transporters that we wanted to use, obviously, if you want to use for drug delivery, they should be non-toxic. And so to ensure this, we wanted to make sure that our transporters only transport these anionic drugs, but do not transport chloride, because that would make them toxic. You start to mess with the concentration gradients in biological systems. And so we went back to those very simple diphenylureas that I showed earlier on for the sensing system, because we already knew that they don't transport chloride. As you can see here, they do not transport chloride. There's no chloride transport for them. Now, in terms of drug transport, the first one we tried is probably the easiest, the simplest carboxylic acid-based drug, salicylic acid, which is the active compound for aspirin. By itself, salicylic acid has a small background permeability through the membrane, but when we add these transporters, it goes through the membrane considerably faster than without transporter. Now, we've done this assay with all of these 13 drugs. I'll just show you the results for one other one, like valsartan. Again, it has a very slow background permeability, but when we add transporters, especially the unsubstituted one, it is enhanced. So we have this enhancement of membrane permeability. And to quantify this a little bit better, we calculated the initial rate of transport in the presence of transporter as well as in the absence of transporter, and then the ratio is a sort of enhancement factor. And so when we plot the enhancement factor as a function of HPLC retention time, so we used HPLC retention time as a substitute for the lipophilicity of these different drugs. So the results here are shown for the enhancement that is achieved by this 1,3-diphenylurea for a variety of drugs. And so what you can see is if you have really polar drugs like diatrizoate and amoxicillin, the enhancement is very minimal. And this is, we might be able to transport them if we would add higher concentrations of transporter or if we would add more active transporter, but this is quite likely going to be at the expense of selectivity over chloride transport. Now, in the middle is where we get most of our enhancement. So for these molecules with sort of intermediate lipophilicities, we can get big enhancement in terms of membrane permeability. Now, at the other end of the spectrum, you see it slopes down. So really highly lipophilic drugs are not really have a big permeability enhancement based on these transporters. And this is actually not that strange, because if the drug is already very lipophilic, it goes through the membrane unassistedly, relatively easy, so you cannot get a huge enhancement anymore. Now, what is actually really interesting about this particular graph is that 1,3-diphenylurea, the transporter that we use, is actually a plant hormone that is present in, for example, coconut milk. And so this means that if we can have small molecules that have such a large effect on the membrane permeability of known drugs, that means that rather than just using them for drug delivery, it also means that there are probably small molecules present in the food, as well as in maybe other drugs, that help with permeability of other drugs. And this means that this is a very underexplored type of food-drug or drug-drug interaction, which is something we would like to investigate a lot more in the future. And so this kind of leaves me now with my conclusions. So I hope I was able to show you that you can use transmembrane transporters to increase the selectivity of optical sensors. We can do this without negatively affecting sensitivity. Sensitivity is unaltered. If anything, the dynamic range is actually improved. And we were also able to show that you can use transmembrane transporters to increase the membrane permeability of anionic drugs, which could have implications for drug delivery, as well as food-drug or drug-drug interactions. And so this just leaves me in thanking my group, which is kind of shown here. I currently have 5 PhD students. So Salam has done the drug delivery stuff. Sarah Marshall has done the sensing part, and the other 3 students, as well as my postdoc, are working on unrelated projects. I also want to thank Tulane University, as well as the Louisiana Boards of Regents for funding. And obviously, I would like to thank everybody in the audience for listening to my talk. And so I will be happy to take questions if I can get out. So if anyone has any questions, they should be on the chat, and Fraser should find them.
Fraser, can you unmute yourself?
Now I can. Can you hear me?
Yes.
Yeah. All right. Okay, Natalie, thank you very much. A very clear discussion of your transmembrane and drug delivery work. We actually have one question here already, maybe more. Yeah, there's more. Let me start off with one from Andreas Gentesh. By using membranes and sensing systems will strongly be affected, that is, the quality of the membrane. I guess what he's saying is, what is the role of the membrane, and can it vary a lot? Notably for mixed compositions like EYPC, would that be an important issue? Notably using initial rates. I hope that's understandable.
All right. So at the moment, we have used EYPC, which is not a pure membrane mixture. So it is about 95% POPC and 5% other lipids. We would like in the future to try the effect of membrane composition, largely for the reason that phospholipid-based membranes are not all that stable, so you would have to make them for the sensing. So if we want it commercially available, we probably want something a bit more robust. So we want to try different membrane compositions, but we haven't done it yet.
Thank you, Natalie. We have another question here from Thushar. The transporter has to be tuned for whatever drug is to be used, right? Have you tried the drug delivery with any other drugs?
At the moment, we are trying phosphate-based drugs as well. We would like in the future to see if we can use it for cationic drugs. Cationic drugs are usually not that much of a problem for membrane permeability because their pKa, if it's it's usually an amine, so their pKa is around pH 7, so that helps with membrane permeability. But we'd like to expand our range. We did try very considerably to have something that would be selective for anionic drugs so that it's not tailored very precisely to one single drug, because that would not be very useful, because then you would need, if you do a formulation, you would need FDA approval for every single transporter that you use. So we want something that is FDA approved as a drug delivery system that can be used for multiple kinds of anions. It's more of a class of drugs that we would like to target. So something that would transport carboxylic acid-based drugs, maybe dicarboxylate-based drugs, cationic drugs, guanidinium-based drugs, and so on.
Thanks, Nathalie. Here's one from Matthew Serta. Nice talk. For the drug delivery approach, is there a benchmark association constant you must meet to facilitate transport?
So most of the work that has been done with anion transporters seems that the effect of lipophilicity seems to be a lot larger than the effect of the binding. We can get too weak on binding, and you can get too strong on binding, but within that, the lipophilicity seems to be more of the overruling factor, more than the ability to bind the anions. Probably in the future, we will try to figure out if there is a benchmark, but most likely it will be different per drug and per transporter used.
Okay, Nathalie, I think this is going to be the last question. Time is marching on. From Joseph Michel. Great talk. For oral drug delivery, what do you think the effect of gastric pH will be on the supramolecular complex of ureas with carboxylates?
So most likely in the stomach, the carboxylates will be neutral. And so there will be very little effect there. So most likely we would assume that the uptake or the enhancement in permeability will happen further downfield at the intestines, where we have more neutral pH.
Well, thank you very much, Nathalie. It's been an inspiration to listen to you, and I have learned a lot these last 25 minutes. So now you can relax, and I'm going to go and introduce our next speaker, Carson Bruns.
Thank you, Fraser.
So Carson Bruns is hailing from the University of Colorado. He's at the Interdisciplinary Atlas Institute. And he is someone I would describe as a chemist-cum-artist. He uses nanoscience to invent emergent materials and technologies. And he is a creator of color-changing tattoos, believe it or not, and also shape-shifting molecular machines. So Carson is, without a doubt, a proud Coloradan, or maybe it's Coloradonian, I'm not quite sure. He was brought up in Colorado, that goes without saying. Nonetheless, he went to Decorah, Iowa, to Luther College, a liberal arts college, to have the experience of his first degree. I've actually been there in late summer, and it's completely surrounded by green fields of maize, as far as you can see. So Carson has Luther College to thank for honing up his interest in art as well as in science. I reckon he also got a good grounding in English language and literature. We'll come back to that later. On graduating from Luther College in 2008, he arrived at Northwestern, where he decided that it was not enough to have one advisor, he needed two. I was one, and Sam Stoop, my colleague, was the other. So in this particular instance, I've got to say there wasn't a lot of collaboration, which is rather unique. Sam and I have collaborated a lot between the work that Carson was doing with Sam and Carson was doing with me. It was almost that there were two independent lines. And so in 2013, when Carson graduated, one could say he was a double PhD, or call him a PhD squared. And so during this time, with me at least, he netted 21 publications, and probably quite a few more with Sam. But that was only the tip of the iceberg. During his time with me, and this started quite early on as a result of an invitation I got from Luigi Fabrizi from the University of Pavia to contribute a chapter to a book on beauty and chemistry. So naturally, I went to Carson, given the fact that I knew he had this background in the arts, and said, would you like to assist in writing this chapter? And we've got very close to the deadline, about 4 weeks away, and I started to panic. I thought, I haven't seen and I haven't talked to Carson about this article. What should I do? Well, obviously, I go and speak to him, and he says, Fraser, relax, I've written it. And not only had he written it, but when I saw the product, it was word perfect. And so there was no longer a panic in my breasty, to use a Scottish phrase. So after that, a little later, we reached a situation where I would return to Carson. I said, would you fancy taking up the writing of a book about the mechanical bond? And again, without hesitation, he said, sure. And again, he took off like a rocket. And before I knew where we were, we had, well, it took a year and a half, approached about 800 pages of text. That is book text. And we had to jettison the last chapter on applications of the mechanical bond. So in many ways, it is quite remarkable how he can produce so much in such a little time. I don't know if people can see this, but this is the book I'm talking about. And if during the pandemic you need a good read, here's Carson's book. Have a read of it. So it has almost 1,000 illustrations, again, done in his own fair hand. After he left Northwestern, having had this book under his arm, he took up a prestigious Miller Fellowship at Berkeley with Matt Francis as his mentor. And this is where, again, he was able to broaden his experience, because he was surrounded by a cohort of mathematicians, physicists, astronomers, biologists, and even chemists. Therefore, transformation that he needed to make was to keep that kind of interdisciplinarity going. And I think he was pretty delighted when he got an offer from the University of Colorado to go there in 2017, as I said before, to the Interdisciplinary Atlas Institute, which is absolutely brimming over with colleagues that are artists, designers, roboticists, engineers, you name it. And so without any more ado, over I go to the Coloradan, Carson Bruns. The stage is yours. Over to you, Carson.
Well, thank you so much, Fraser, for the very kind introduction and the walk down memory lane. Those are very fond stories for me. And it's my pleasure to be here. Thanks also to ChemPhysChem for organizing the symposium and letting me share the work we've been doing with you on self-assembling and interlocking polycyclic aromatic hydrocarbons. I'm excited to share this work because it's the first time I've shared it publicly, even though we've been working on it for over 2 years now. And it's all unpublished work, but since it's been a long time coming, I hope that we'll get to communicate it soon, not only through the seminar, but in the literature as well. I like to start my talks by thanking my lab. This is my lab. So I start with the gratitude section. This is a fantastic group of people. We are, as Fraser said, in this interdisciplinary place called the Atlas Institute. And so this is a very diverse team of mechanical engineers, material scientists, physicists, and
Carson, we can't see your
chemists. Oh. Very sorry about that.
But we can see you, Carson. We're not sorry about that. Take your time. There we go.
Here we go.
Thank you.
Great, thank you.
Can you see my slides now? All right, thanks. Yeah, so this is my team, and very grateful to be working with these folks. Most of the work I'm going to be sharing today is Hagen's work, the postdoc in my lab. But our team works in kind of three domains. We have a biomedical tattoos domain, so we're trying to engineer tattoo pigments using chemistry and nanoscience to confer novel health benefits. And then we have a team working on slide ring nanomaterials, so basically cross-linked polyrotaxane elastomers and gels. And then the work we'll be talking about today is the machines domain, which is really across all length scales. So of course we're doing things on the nanoscale. We're interested in molecular machines, and that's where our focus will be today. But we're also doing things on the microscale. We are building machines that can pattern microscopic hydrogels into any two-dimensional shape, and we're trying to self-assemble those into microscopic machines. And we're even building robots that can automate chemical synthesis. So this is the kind of breadth that an interdisciplinary institute can afford you on your team. But again, this is a ChemPhysChem seminar, so we'll try to stick to the molecules today. And the two domains of molecules that I've been interested in ever since I was a PhD student in Fraser's group and Sam Stoop's group are mechanomolecules, as I like to call them, rotaxanes and catenanes, and organic semiconductors. And they both have their own kind of unique domains of interesting properties, right? On the mechanomolecule side, we have very interesting structures and dynamics, and of course, stimulus-responsive behaviors in the case of molecular switches and machines. And on the organic semiconductor side, we have really interesting photochemistry, magnetic properties, conductivity, electrical and thermal, as well as stability, which can be tuned from very unstable to extremely stable. And so I think that merging these two domains could lead to materials with emergent properties. And so this is kind of where we're focusing right now. There are a handful examples of completely pi conjugated catenanes. So if you go in the literature, you can find 5 or so papers where both rings of the catenane are completely pi conjugated. There's an uninterrupted pi system in the full backbone of the ring. And this is beautiful work that's inspired us. That's not quite the case in rotaxanes. There are many, many examples of highly pi conjugated rotaxanes, especially where the dumbbell is highly pi conjugated, and a few examples where the ring is highly pi conjugated too. But in all cases that I'm aware of, there are still insulating moieties somewhere in either the ring or the axle. So we haven't seen any rotaxanes that I'm aware of that are completely pi conjugated without any insulating moieties anywhere. And so that's kind of a target for us. And so we focus on cycloparaphenylenes because they're these fantastic molecules that have kind of gone off like a rocket over the past decade, where they've gone from kind of intellectual curiosities in 2008 to commercially available products now. And they come in a wide range of sizes with tunable diameters and band gaps, which is great. They're very rigid, so that affords a lot of pre-organization in the context of host-guest chemistry, right? If you have an appropriately size-matched guest, it can bind the cavity of a CPP, as I'll call them, with very low entropic penalty, and in the right solvent, it can even be entropically favorable to bind something this rigid. And of course, they're lined with curved pi surfaces, so there are a lot of sites for pi-pi and CH-pi interactions available. And the supramolecular chemistry of CPPs has been known for almost a decade now. They've been known to bind fullerenes, and there's a kind of a large family and pretty sizable body of literature on fullerene CPP complexes, but not a whole lot else going on yet. And as I mentioned, these are commercially available, which we really like, because then we don't have to spend all of our time synthesizing them. We can just buy them and get on with the chemistry that we're interested in doing. So I've been really inspired by these so-called nano-Saturn complexes of fullerenes and CPPs. There's a lot of them that have been reported over the past decade, and even on the bottom, some CPP relatives that also bind fullerenes very well. And when I started my independent career in 2017, I was inspired by this work and wanted to see if we could expand the library of guests for CPPs beyond the fullerenes. And so we just started kind of trying things. And we started with ferrocene and 8-CPP, and I thought, based merely on intuition, that perhaps the ferrocene CP rings could engage in pi-pi interactions with the paraphenylene rings of 8-CPP. And so when Hei-Jin joined the lab in early 2018, this is what she started with, and we mixed ferrocene and 8-CPP in chloroform, and we got a very modest change in chemical shift that actually increases with increasing temperature. So you see larger changes in chemical shift at elevated temperatures. Again, they're quite modest changes, but changes nonetheless. And you can detect a one-to-one complex by mass spectrometry, also by job plot, which I'm not showing. And if you do an NMR titration, you can get a binding constant. Again, it's a very low binding constant on the order of 50 inverse molar by NMR, which might be a slight underestimate. We can also estimate the binding constant by fluorescence titration because ferrocene quenches the emission of 8-CPP. And you kind of overestimate the binding constant in that case because of nonspecific interactions. So on the order of maybe 100 inverse molar for the binding here. But we were actually able to grow single crystals of this compound. And to my surprise, at least at first, we found that it is not stabilized by pi-pi interactions, but rather the ferrocene unit is tilted by 45 degrees so as to direct its CP protons into the aromatic faces of the 8-CPP rings phenylene units to engage in CH-pi interactions. So this structure is stabilized by 6 CH-pi hydrogen bonds. And there's some other interesting things about this structure as well. Here's my nod to ChemPhysChem. There's a paper in 2013 that found that the quinoidal character of the cycloparaphenylenes increases as size decreases. So as you get to smaller and smaller CPP rings, the difference between the C1, C2, and C2, C3 bond length becomes more dramatic, indicating that you have a higher quinoidal contribution to the resonance structure, which of course affects its band gap, which is why the smaller CPPs have much lower band gaps than the larger ones. And what we found, if you compare the solid state structure of 8-cycloparaphenylene to our complex, is that that quinoidalization is reversed upon binding. So in other words, the ferrocene guest re-aromatizes the 8-CPP ring, and it does it significantly, such that the 8-CPP ring has more aromatic character, significantly more aromatic character, even than like the very large cycloparaphenylenes. So that's interesting to us because it means that you can use gas binding to tune the band gap of these materials, and we'll come back to that. But this, of course, got us really interested in the CH-pi interaction in the context of CPPs, and in the interim, a number of papers have come out that have reported CH-pi interactions stabilizing inclusion complexes of the cycloparaphenylenes, and this has just encouraged our work even further. So we've been looking at a number of polycyclic aromatic hydrocarbons as CH-pi stabilized guests for the cycloparaphenylenes, and we started with corannuline on top and coronine on the bottom. And we mixed these two compounds with 10, 11, and 12 CPP, and we found that in the case of corannuline, you get a precipitate in chloroform only when you mix it with 10 CPP. In the case of coronine, you get a precipitate in chloroform only when you mix it with 11 CPP. So there's this specific sort of size selective matching here that leads to a precipitate, which we assume to be the complex. And you can detect these one-to-one complexes once again by MALDI mass spectrometry. We can't really get NMR spectra in chloroform because of the precipitation, but at low concentrations, these complexes are soluble enough in dichloromethane and dichloroethane tetrachloroethane to get NMR signal. So again, we can do our NMR titrations and estimate the binding constants, and we're getting higher binding constants here than we were in the case of ferrocene, presumably because there's more CH-pi interactions on the order of 500 and 2000 inverse molar, respectively. So we weren't able to grow crystals of these compounds, so we turned to DFT calculations, which was a very convenient thing to do during our lab shutdown related to the COVID pandemic. And the first thing we learned is that you need to use a long-range corrected functional. If you use the kind of standard, really popular B3-lip 631G method, you wind up with energy minimized structures that are not so reasonable because that functional doesn't really correct for long-range dispersion interactions. It doesn't really capture dispersion interactions very well. So we use these LC B-lip. LC stands for long-range corrected functionals that give us some very reasonable looking predictions for the energy minimized structures of these compounds. And they predict that choranilene has 10 CH pi bonds and choranine 11 CPP has 11 CH pi bonds. And we use both the Brandl-Weiss and the CH pi systems of determining cutoff values for what is a CH pi bond. These are two completely independent and geometrically unrelated methods for determining if there's a CH pi bond or not, although they more or less agree with each other all of the time. And so we use both, and we find that we have good, relatively strong CH pi bonds in both of these complexes as predicted by DFT. We also use DFT to validate our method by comparing the energy minimized structure of the ferrocene ACPP complex with that of the X-ray diffraction solid state structure that we determined. And we get very good agreement. Again, 6 CH pi bonds in both cases with very similar bond angles and distances. So we think this method is a fairly reliable way to predict these structures. And so that's what we're using as we go forward, but not as great at predicting binding energies. The method definitely overestimates the binding energies of these complexes. Even if we do solvent corrections in chloroform or basis set superposition error BSSE corrections. But it does predict their relative stabilities very well. So the DFT predictions suggest that the relative stabilities of these complexes are in good agreement with our actual measured relative stabilities. And so it might be possible to simply multiply our calculated binding energies by a scaling factor to predict the sort of binding constant that we'll observe, but that remains to be seen. And that's what we're working on now. We're going through all these commercially available polycyclic aromatic hydrocarbons, and we're predicting their structures and then getting into the lab and measuring their binding constants and seeing how well they agree and whether that hypothesis is true or not. And so we have to use this selection criteria, which is written out on the left-hand side in the green box, which is a very simple hypothesis and quite reasonable, I think, that any guest that's going to bind well by CH pi interactions inside of a CPP host should have a distance, should have a diameter that's approximately 2 CH pi bond lengths smaller than the diameter of the CPP ring, so that it can engage in multivalent CH pi interactions across the cavity of the CPP ring. So based on the literature on how long a CH pi bond length is, it's somewhere in the range of about 2.35 to 3.1 angstroms. We multiply that by 2 and we say any polycyclic aromatic hydrocarbon with a diameter that falls within this range of 4.7 to 6.2 angstroms should bind well within its respective cycloparaphenylene ring. And so we've kind of performed this size matching algorithm on the commercially available polycyclic aromatic hydrocarbons you see before you. And we've calculated a lot of these structures already, although this work is still ongoing. And indeed, the algorithm works. We see this kind of Goldilocks effect where guests that are size matched according to this kind of selection criterion are the sort of Goldilocks complexes. If you have a CPP ring that's too small, you get a sort of much lower binding energy. And if you have a CPP ring that's too big, you still get binding and it's reasonable, but it's weaker than in the size matched one because you lose out on some of the CH-pi interactions that would have been possible in the appropriately size matched host. So it works for planar guests like chlorine. The same thing also works for non-planar guests like helicine. And so we've been waiting for helicine to arrive in our lab for almost 2 months now. We ordered it a long time ago, and we've been really excited to test this complex because this is the first one that we really predicted and said this is going to be a very stable complex, but we haven't been able to kind of check yet. Anyway, like I said, we've calculated these minimized structures for a lot of polycyclic aromatic hydrocarbon CPP host guest complexes, and we find that if you just plot the total number of pi electrons against the predicted stabilization energies, you get a fairly linear relationship for the polycyclic compounds. And it actually works better to plot it this way as a function of the total number of pi electrons than it does to plot it against the number of CH-pi bonds. So you still get increased stabilization as you increase the number of CH-pi bonds, but the number of pi electrons in the system is a better predictor of the stability than just the number of CH-pi bonds. So that's kind of our approach to the CH-pi complexes, but when we started this work, we were interested in pi-pi stabilized complexes. And so we imagined that you could use the same approach to select pi-pi stabilized cycloparaphenylene complexes as well, except you have to just use a slightly modified range, right? Because the pi-pi bond length, the plane-to-plane distance in a pi-pi interaction is more on the order of 3.2 to 4 angstroms. So our algorithm selects, our size matching criterion selects between 6.4 and 8 angstroms so that you can have 2 pi-pi bond lengths. And you'll find that the fullerene complexes with 8 CPP all fit this criterion. But again, not a lot of other options yet for non-fullerene host guest complexes. So we decided to look at oligoacetylenes as guests for 5 CPP and 6 CPP. The acetylene unit being a very small linear molecule will fit inside of, in principle, either the 5 CPP or the 6 CPP ring so that it can engage in multivalent pi-pi interactions. And so we've been looking at a sort of family of these complexes as well, where we take an oligoacetylene and it may have an aromatic stopper or not on it. And again, we plot the predicted stability of these complexes against the number of pi electrons. And again, we find a pretty linear relationship here. You can slice this data up in all kinds of ways. For example, if we hold the dumbbells constant and we just compare 5 CPP and 6 CPP, we actually get higher stabilities for the 6 CPP complexes, presumably because there's more electrons in the pi system and this is a dispersion interaction. But it may also be because of some penalty for reorganization in the highly strained 5 CPP macrocycle to some extent. But you can also look at the effect of different axle sizes, right? You get higher stabilities with longer axles, but you get diminishing returns there, especially when you get out to 4 and 5 oligoacetylenes in the axle. And the stopper size, right, as you fuse more rings to the acene stoppers, you get higher stabilities. But this only works for linear acenes. You get outliers on this plot if you turn to things like parylene or triphenylene, which seem to have roughly the same stability of naphthalene and phenylene, respectively. So we're definitely uncovering some patterns in this system, and we're in the process now of trying to confirm them in the lab. And so we're taking these forward, and we want to demonstrate applications of these complexes as well, of course, and we think that some of the application areas for them could be in the stabilization of highly reactive species, such as radicals or explosive oligophenylenes, polyphenylenes, rotaxane synthesis, and 3-dimensional organic semiconductors. So we've been making rotaxanes from a formulated ferrocene 8 CPP complex, and that seems to be going reasonably well. We've started trying to make rotaxanes from the oligophenylene 6-CPP complex, and we can detect them by mass spec, but we get very low yields. It's hard to isolate them. So we use this kind of plot to remind ourselves when you're in these sort of low binding regimes, because we're on the order of like 10 to 100 inverse molar, you really have to use either very high concentrations or very high excess. And keeping that in mind, we've been able to go back and also enhance the stability of the complexes. And so now we're making these anthracene stoppered rotaxanes in the lab, basically as we speak. And what we lose in our yield in terms of having a relatively low binding interaction, we'll gain back in the rotaxane, because when you have these rigid components and high, like a lot of low affinity binding sites, you're going to have really low barriers to shuttling, which means you should have very fast dynamics. And of course, they're all pi conjugated. So wouldn't it be interesting if, for example, you could transport holes through the paraphenylene networks and electrons through the axial networks, for example? This is just a concept right now, but that's kind of where we're going. In order to do that, you have to do band gap tuning, and we found that that's very possible, again, in the ferrocene case, but is also in the coronine and coranulene cases. One thing that's really interesting is that the coronine 11-CPP complex, the HOMO lives completely on the guest and the LUMO lives completely on the host. And so you might have some interesting charge separation and splitting processes there as well. So I've reached the end of my talk, and I want to thank all of you for your time and attention, and especially big thanks to Haejin Kwon. She's an amazing researcher, and I'm just super impressed by her talents and her skills and her intellect. I'm just so blessed to have her on my team. So with that, I'd love to answer any questions.
All right. Thank you, Carson, for removing your slides and for a wonderful presentation. We heard you in another context just a few weeks ago. You are moving very quickly on the rotaxane front as well as on the other front. There's a question here I'm going to take first because it's from Steve Goldup. Carson, could you use the formation of host-guest complexes to separate a mixture of CPPs, perhaps by mounting the PAH on a solid support?
Yeah, that's a good question. I think so, but the challenge there for the CH-pi stabilized ones is that if you were to functionalize any of those places where a CH bond is, you're going to kind of destroy the interaction, and the guest is going to become too big for the host. You're going to really lose your binding affinity. So it'll work, but only in cases like the helicene, right? If we use to functionalize helicene and we functionalize one of the sites that's not pointing into the paraphenylene rings, then perhaps we should be able to, kind of pull selective CPPs out of a mixture. Or likewise, we could use CPPs to pull, polycyclic aromatic hydrocarbon pollutants out of cooking oil or a water supply or something like that. One thing that's really cool about the CH-pi interaction is that it works in polar solvents. It's not really diminished in polar solvents. So we can expect these, if we can make them soluble in water, to work really well or perhaps even better in water due to an added hydrophobic effect.
We have a related question from Corentin Busschaert. Carson, could you use your CPP Ps to separate fullerenes?
I believe so. Especially if you had them into a kind of linked into a solid support or a network or something like that. But a number of other researchers in the community have already shown that that's possible, that you get sort of size selective encapsulation of fullerenes with different CPPs. So I think other people might be working on that.
And a question again from someone we had earlier, Andreas Gentish. Carson, wonderful work. I'm curious about the mechanism for precipitation in chloroform and not in dichloromethane. It is a remarkably small difference. Have you considered oxidizing the CPPs to see if the number of pi electrons presumably are able to stabilize the system even more?
Yeah, I have to correct myself a little bit. So the core aniline tin CPP complex, I think my postdoc has just informed me, is actually somewhat soluble in chloroform still. So it's not as insoluble as I claimed. At high concentrations, you do still get precipitation, of course, but there is some solubility in chloroform as well as in dichloromethane. Not really the case for coronine 11 CPP. It really does seem to pretty much just precipitate in chloroform. And we don't really know why that subtle change in solvent leads to that big of a difference. But the solubility is low in dichloromethane as well. So it might be a subtle difference in solubility. We have not looked at oxidized or reduced versions of host or guest yet. We're definitely interested in that as well. But we have to kind of finish up our work with the neutral species first, I think. But thanks for the suggestion. We'd like to look into that.
A question from Chunyan Lin. I'm curious about generating supramolecular charge transfer emission by incorporating electron donating groups on CPPs and pairing up with electron deficient guests.
Yes, there's been a little bit of work by other folks in the community in that direction as well. And I think if you go that route, you'll definitely find enhancements in stability. But the sacrifice you make is that you can no longer use these commercially available CPP rings that you can just buy from TCI, right? Or you can buy them and then you'd have to modify them somehow. But we really like to just sort of buy these off-the-shelf materials and get straight to work with them. And I believe that there's a really, large, so that's where we're starting. But I think there's a really large possibility, like a really large parameter space you can probe for, are there Hammett correlations when you put electron donating or electron withdrawing groups on the stoppers, for example? Or to the guests. And there's a lot you could do there to probe structure property relationships here. Good question.
Another question, Carson, from Oleg Borodin. Thanks for a great talk. What about, it jumped. What about the stability of the oligoacetylene-based rotaxanes? Obviously, the ring stabilizes the thread, but blah, blah, blah.
Yeah, we think the reason, so when the first rotaxane we made was a it was a dodecahexatriene capped by phenylene rings, and we were unable to isolate it, and we think the main reason was because it was polymerizing still. So the ring helps stabilize it, but it only covers about, a third of the axle. And so the other 2/3 of the axle is still open for polymerization, and the compound decomposes quickly. So that's why we're making rotaxanes with shorter axles now, which should have higher stability, but I can't comment on that yet. We expect they'll be much more stable as the axles get shorter, because the rings can protect more of the axle, and also because they're just less reactive as the axles get shorter. But that's the real challenge here, is finding the balance of a long enough axle that you get a good stable threaded complex, but a short enough axle that it doesn't decompose when you're finished making your rotaxane.
And now the final one from somebody who thinks that there might not be time for his or her question. I think. Adrian Rosby. Probably not time for the question, but could ferrocinium be a suitable guest for the CPPs, considering possible pi-cation interactions?
Yeah, thanks for that question. So we're interested in, and also once we have the rotaxane, we're interested in oxidizing or reducing the ferrocene unit to hopefully shuttle the ring back and forth, right? We'd like to make molecular switches. And so I think so. But we haven't checked yet. That's just harder experimentally to do. But and even to calculate for us, but we're working on it.
Okay then, Carson, there are lots of questions that I would like to ask myself and from others, but we have to close the question and answer down with a big thank you to you for treating us as always to a wonderful presentation. Thank you. So now I'm going to introduce our last speaker, Steve Goldup from Southampton University. So Steve began his independent academic career at Queen Mary College in London. And it was there after 6 years where he was, first of all, a Leave of Hume Trust Early Career Fellow, and then a Royal Society University Research Fellow, that he moved to Southampton to be an associate professor in 2014. He was promoted to a full professorship in 2017 and was awarded a Royal Society Wolfson Research Fellowship only last year. I regard Steve Goldup as the world's leading research and person in research and authority on stereochemistry of the mechanical bond. That's in fact the subject in Carson's book here in chapter 5, which at the time of its being written, Steve was a very welcome reviewer of that chapter, for which Carson and I were very, very thankful. Now, I have to say, in a very general way, that I believe that stereochemistry has got an enormous fill-up. It has gained a new lease of life from the invention of the mechanical bond. Gone are the days when we just have to rely almost solely on stereogenic or centers of chirality. What the mechanical bond has done for us is to open up the whole chest of stereochemistry to axes of chirality, planes of chirality, and even helical chirality. And that's what Steve has been doing in a very elegant way. A little story about how Steve sort of entered the field of research that he's known for. Steve's group first got into chiral interlocked molecules because of a dirty NMR. A student purified a sample several times because it had too many signals. Then after taking a closer look, realized it wasn't dirty at all. It was just that it had been desymmetrized by the stereochemistry in the molecule. And this got Steve and his student thinking about how different sources of stereochemistry interact in interlocked molecules, and ultimately led to their famous auxiliary approach to produce optically active chiral retaxanes in particular. And Steve comments that when things don't look like what you expected, that's when the good science often starts. Okay, so excuse me, I lost some notes for a minute. So your first exposure, a little bit of an anecdote here, to catenanes, you concede, Steve, was on a visit to Birmingham in 1995 when you were looking for a place to do your undergraduate work. And you reckon it was one of my postdocs that gave you a presentation on catenanes and retaxanes, and you still remember that quarter of a century later. So that started what you describe as a niche, and it took a long time to scratch. You admit that you talked to Harry Anderson during your part 2 at Oxford, where you did your first degree, and that, however, didn't change your approach to chemistry. You still stayed with what you call the standard organic training, first with Jack Baldwin at Oxford, and then with Tony Barrett at Imperial. But while you were with Barrett at Imperial, you started reading about molecular machines. And you finally succumbed to the urge, and you headed north to the Athens of the North, i.e. Edinburgh, which will soon be a real capital city in its own right, because Scotland will seek independence, I predict, quite soon, so that this enlightened country and liberal country to the north on this little island will be able to seek to join the European Union. However, returning to Steve himself, he after his time with David Lee in Edinburgh, 3 years, he of course returned to London, to Queen Mary, which I told you about, then on to Southampton. And just to sum up, mechanically interlocked molecules with unusual stereochemistry that allow him to study sensors, catalysts, and materials in general is his everyday love in chemistry these days. So the title of Steve's talk is Synthesis and Applications of Interlocked Molecules. So the screen is yours, Steve. Please take over.
Right, need to do things in the right order. Thank you very much for the exceptionally kind introduction, Fraser. A real honour to get those kind of words from you. And can everyone see my screen?
Yes.
Perfect. Just thought I should check. So yeah, absolutely, really kind introduction, and yeah, it was a real reading the chapter on stereochemistry in the Bible of the mechanical bond was a really nice way to get an overview of the field, and I think it's still really the place to go if you want to know about the history and the kind of future of mechanically bonded structures. I would really start with that book. Just a little plug there, with the two authors in the audience. I think that's quite appropriate. Before I start, I'd just like to say it's great to have questions in the talk, but if anyone has any questions after the talk that don't get answered, I'd be happy to answer them on Twitter. So I've put up my Twitter handle there. And of course, that applies to people who are watching this on the video later. So, Carson's given a really nice introduction to the mechanical bond. I'm not going to go over it in a great amount of detail. On the left, we have a catenane, which is two rings, which are threaded through one another like links in a chain. On the right, we have a retaxane, where we have a macrocycle on a dumbbell-shaped axle. And these are really famous as components of molecular machines. Carson kind of alluded to some of that stuff. Fraser, obviously, is the progenitor of the field, or one of the progenitors of the field. And this is all about the movement of the components. And obviously, I did a lot of work on that with Dave Lee. But thinking about my background, coming from kind of a very, I don't want to say standard because that sounds derogatory, but from a traditional organic synthesis background, I've been playing with these molecules for a while. And the thing that struck me is there's some chemistry to be done here. And the chemical opportunity that I saw and what I wanted to exploit at the start of my independent career was the fact that when you thread one molecule through another, you create a 3D object with a crowded, flexible environment, which is kind of created between the two components. And that crowded, flexible environment has the potential to be used for chemistry. And the kind of things we were hoping to use it for: develop new sensors, electronic materials, do some unusual coordination chemistry, and play with some catalysis, among other things. And I have to say that we're not alone in this. So Carson looks like he's Lobitus on the electronic materials front, I have to say, just having seen his lecture, really beautiful stuff. Paul Beer was developing sensors based on interlocked molecules. Coordination chemistry really goes back to the start of the field. And catalysis is something that's really taking off at the moment, with people like Jose Berna, Dave Lee, Jochen Niemeyer. There's lots of people who are getting interested in these sorts of things. And the thing that I like about this is it allows us to kind of unify the interest in all of these applications with my kind of core interest, or the thing that I find really fun, which is synthesis and methodology, coming up with ways to make molecules. And you can't do any of these applications if you can't make the structure you're interested in. So you have to have good ways to make your molecule. And once you have it, you want to do cool things with it. And the reaction that we use to make our molecules, again, we didn't invent it, but I would say that we've optimized it really quite heavily. So the first report of this active template synthesis was by Dave Lee in 2006. And the version that's on the slide here is actually our version. And the original version worked very well. You had to put a large excess of stoppers in some case. So the stoppers are the alkyne and the azide. You had to put a large excess of these in to get the reaction to go to quantitative yield. And we played around with things a little bit, and we have a system now which can give us quantitative yield pretty much with one equivalent of all the components. And that's something we published back in 2011. And the reaction works by coordinating the copper inside the cavity of the macrocycle. And then all you're doing is the standard copper-mediated triazole formation. But of course, because the copper is embedded in the macrocycle, your reaction happens faster through the cavity of the macrocycle than anywhere else in solution, and ultimately leads to mechanical bond formation. So our first fiddling or optimization with this reaction kind of led to these quantitative yields, but there were lots of limitations still. And over the next kind of 4 or 5 years, we kind of fixed the rest of the limitations, because it was really important for us to have a reaction we could just use to make things with control over structure, good general substrate scope with respect to the alkyne and azide, respect to macrocycle structure, getting the reaction times down, and then having very readily available starting materials. When we started, we had readily available alkynes and azides, but the macrocycle was very hard to make. And now we can actually make macrocycles on gram scales. That's really accelerated our research. So I just wanted to kind of maybe highlight this as, if you want to be able to use something practically, you have to kind of optimize every single feature of the system. And it turns out that once you've optimized all those things, you can extend it from ritaxane to catenane synthesis really effectively. And again, this had been done before, but in these optimized systems, we're now getting near quantitative yields, often with very low equivalents of the alkyne azide precursor. So this is now a really practical synthesis of catenanes. And having done that, we can start thinking about the applications. So we've gone back and done some coordination chemistry. So on the left-hand side, we have a really unusual copper 2 complex where the copper is almost tetrahedral with a very, very long contact to the perchlorate anion. And this kind of starts to look like the kind of metal ion coordination environments you get in proteins. So you can distort the metal ion coordination using the confines of the mechanical bond to enforce the coordination geometry. Now, on the right-hand side is some work we've been doing with Gareth Williams up in Durham, looking at platinum coordination chemistry and using the mechanical bond this time just to stabilize the complex. So this triazole ligand is not a very good ligand for platinum. It's relatively easy to displace, but in the interlocked structure, it's incredibly robust. And so this is a potential application of the mechanical bond in coordination chemistry. I should say the stuff on the left-hand side was done in collaboration with Maxi Rössler at Imperial College. I should acknowledge that as I go through. And then just one last kind of general example, just to show you how powerful this methodology is. We've applied it to the synthesis of mechanically interlocked DNA. So this is a reaction that can work under relatively dilute conditions and in water, and we can get very, very high yields of the mechanically interlocked DNA where we're threading the macrocycle around the main chain of the DNA molecule, and we're replacing one of the phosphate units with a triazole. But actually, Ali Tavasoli and Tom Brown have demonstrated that these triazole-linked oligomers are actually perfectly functional from a biological point of view, so they can be replicated in everything else. But the really nice thing is that once you wrap a macrocycle around this axle, you can shut down PCR. So this is no longer a functional primer for the polymerized chain reaction. And now we're looking at how we can use this mechanical caging of DNA to generate functional molecules for chemical biology and medicine. So that's kind of an overview of some of the things we do, but Fraser's kind of given me quite a strong trail on the stereochemistry side, but I would entirely agree with him that the mechanical bond really does open up new vistas in stereochemistry, and I'm going to talk about some of that today. So hopefully none of you are thinking that this cartoon I have in front of me is chiral, because we can imagine there are lots of mirror planes. There's a mirror plane lying along the axle, and there's a mirror plane that lies flat with the macrocycle chopping it in two. But of course, we can start changing the symmetry of our cartoon. So if I change the two ends of my axles, they're no longer the same. I now still have mirror planes which lie along my axle, but I no longer have a mirror plane that lies flat with the macrocycle. Alternatively, I could keep the two ends of my axle the same, and I could put some sequence information into my macrocycle, and now I still have one mirror plane which is flat with the macrocycle, but I no longer have any mirror planes which lie along the length of the axle. And some of you will have been able to see where I was going with this. If you combine those features, you end up with systems that lack any improper symmetry operations, so no mirror planes, no centers of inversion, and what you end up is with chiral objects. And it's important to note that these are chiral objects regardless of the covalent structure of the molecule, as long as they obey these symmetry properties. So you don't need any covalent stereocenters, no axes of symmetry, no planes of symmetry of chirality even, and no centers of chirality, because these systems are just chiral, just as cartoons. We are not the first people to notice this. I have to really give a history here. So Gottfried Schill was talking about this in 1971, one of the really important key players in the early years of the mechanical bonds. And the thing that we liked about these molecules was that we have a crowded, flexible chiral environment. That's adding one word to that list of properties. That actually chiral is a really important word when you come to organic chemistry or chemistry in general. So we now have this environment where we could think about binding chiral small molecules and looking at diastereoselective binding, or we could start putting a catalytic center in there and seeing if we can generate enantioselective catalysts. And you might be wondering, given the importance of stereochemistry in organic chemistry generally, if people were talking about these in 1971, why has no one kind of demonstrated all of these things already? And the simple problem is that they're very, very hard to make. So the first enantiopure example of a mechanically planar chiral rotaxane was produced by Fritz Wertler in collaboration with Okamoto, and they separated their enantiomers by chiral HPLC. And that's obviously a groundbreaking publication, and over the next 10 years or so, they separated a number of mechanically chiral molecules. But the problem with chiral HPLC is that you are necessarily limited in the scale you can do it on, and you have to be able to separate your molecules, obviously. And the only enantioselective synthesis that have been published was by Professor Takata, and again in collaboration with Okamoto, and they did get a 4% EE. And this is an enantioselective synthesis by definition, but it's not a useful enantioselective synthesis because you don't have a high enough enantiomeric excess that you can use these molecules for any enantioselective applications. And so that's where the field stood when we entered. So the approach we proposed was this idea of forming a rotaxane that has the symmetry properties that allow it to express mechanical planar chirality, but that also contains some covalent stereochemistry kind of represented here by this cartoon stereogenic center. And now, of course, we have two forms of stereochemistry in our molecule. The covalent stereochemistry is fixed. The mechanical stereochemistry we can form in either configuration. And so we have a pair of diastereoisomers. And this is where that kind of accidental stumbling into the field comes in. So when Hisham showed me his NMR, we realized that the covalent stereochemistry that was contained in one of our stoppers was really kind of being expressed into the rest of the molecule. And that suggested that the kind of crowded small rotaxanes we were making basically transferred the information. So the chirality in one part of the molecule was expressed well in the other part of the molecule. And that suggested that diastereoisomerism that we're looking at here might also be well expressed and could lead to separable structures. And of course, once you've separated them, you're into a situation where you have diastereoisomers, which are stereochemically pure. And if we delete in some way, and I'll show you how we do that in a second, the covalent stereochemistry, you end up with your enantiomeric structures. And because they were in separate flasks, you've separated your diastereoisomers, you now have your enantiomers in separate flasks, you have your enantiopure molecules or highly enantiomer-rich molecules at the end. And so that's what it looks like in cartoon form. That's what we proposed. And so Rob Bordoli in my group, this is basically his entire PhD I'm about to show you in 3 slides. I do apologize, Rob, if you're watching. But what he took was a macrocycle that has the right symmetry properties. So we have some kind of sequence information. We have a sugar-based azide, and we have one of our kind of very bulky alkynes. And we just did a simple active template coupling. We got our 2 diastereoisomers, and I can say hand on heart that we often get very lucky in my group. The first example we made separated, which is a really important step in this, and we were not guaranteed separation at all. And then secondly, we were able to crystallize the diastereoisomers to be able to assign the absolute stereochemistry of our molecules as shown here. And so the next step of our synthesis is an aminolysis. And the aminolysis is a great reaction because during the mechanism, if you think about it, nucleophilic attack on the carbonyl-carbon, you go to a tetrahedral intermediate, which then collapses to kick out your alkoxide leaving group. At no point does this not become a stopper. So this remains a bulky group throughout the mechanism. And this is what's called a grafting reaction. And actually, again, with Fraser in the room, and I always do anyway, it's not just because he's watching, this grafting approach was an idea that came out of Fraser's group back at the start of the 2000s. It's a really neat trick if you want to do stopper exchange on a ritaxane. And so we could take our separated diastereoisomers, we could do our aminolysis, and we could get our separated enantiomers. And we got these, I think, in 99% EE and 98.6% EE. And so this summarizes Rob's PhD in one slide. And we have the separated, highly stereo-enriched enantiomers. And this shows for the first time that we can use this simple concept from organic chemistry, which is just a chiral auxiliary, to be able to make mechanically planar chiral ritaxanes. And then about 4 years later, I have to admit, I didn't think it would take this long, but it turned out to be a really challenging problem to crack. Mike and Alberto, along with a lot of other people on this paper, but they were the key movers who got it over the line at the end, managed to come up with a new auxiliary which gives us stereoselectivity in the mechanical bond formation. So we form a mixture of diastereoisomers in that first step, but it's a highly stereo-enriched, I think it's 98 to 2 DR. And then rather than cleaving off our covalent chiral unit at the end, what we do is we symmetrize the covalent stereocenter through alkylation, and we can get through to our highly enantiomer-enriched 96% EE mechanically planar chiral ritaxane there. So what we've done over, it took 5-6 years to get there, but we found a way now of making mechanically planar chiral ritaxanes, which is in theory scalable. We no longer have to go back to chiral HPLC to do our separations. Which brings me to the applications, because the whole justification I gave you at the start of improving synthetic methodology is to be able to get towards applied systems. And so now we had a way of making mechanically planar chiral ritaxanes. We were interested in trying them in catalysis. And so back in 2016, we published a mechanically interlocked gold complex, and we studied its behavior. And what we thought was maybe we could take this concept of the mechanically interlocked gold complex and we could extend it to a mechanically planar chiral interlocked gold complex and look at enantioselective catalysis mediated by the gold. And the reason we thought this might work really well is because we have a problem with gold catalysis that we think we can solve. So gold has a linear coordination geometry. So you have your ligand, you have your metal, and then you have your substrate binding basically 180 degrees. And that often gives you a problem that if you have a chiral ligand, you need to express that stereochemistry well into the substrate binding region. But obviously it's a long way away and it's orientated away from the substrate. And so you often build quite big chiral ligands for gold so that you can reach around your metal to generate your kind of stereo-defined environment. And looking at this crystal structure of the achiral complex, we thought maybe the mechanical bond solves that problem for you pretty much automatically, because the gold is crowded towards the mechanical bond, basically crowded towards the threaded macrocycle. And so we thought any stereochemistry that was contained in the mechanical bond might be well expressed into the reaction space. So Andrew Hurd, when he joined my group, agreed to take on this project. He may not have known what he was getting himself in for, but he took the auxiliary that Mike and Alberto had developed, and he did the active template. He got his 2 diastereoisomers, he separated them, and he got a crystal structure of them as the phosphine oxide. And so that gives us the opportunity to assign the stereochemistry of our mechanical bond. And of course, I haven't shown you up until now, but we do proper stereochemical characterization. We do circular dichroism, and you can see these nice mirror image spectra. And we can do chiral stationary phase HPLC to assign the stereo purity. And we get about a 98% EE of our separated stereoisomers. I just realized I skipped ahead ever so slightly there. I do apologize. I've actually got a typo. These are the diastereoisomers. We have an extra benzar group on here. That's a typo in my slide. I do apologize. So having separated his diastereoisomers, Andrew was then able to alkylate to erase the covalent stereogenic center. And this is really important when you're trying to demonstrate the role of the mechanical bond stereochemistry in catalysis, because there would always be this question about whether the stereochemistry in the covalent unit was influencing the enantioselective catalysis. So we needed to make these systems where the mechanical bond provides the only stereogenic unit. And once he'd done that, Andrew was able to reduce the phosphine oxide to the phosphine and coordinate it to our gold. And now we're ready to do the fun stuff. So we're ready to be able to try the catalysis. So Andrew took his highly enantiomer-enriched, so it's 98% EE gold chloride complex. He treated that with silver, which takes off the chloride. So you remove the chloride anion to give you your cationic gold, and that's generally proposed to be the active species when you're doing gold catalysis. And the reaction we chose was this reaction of a propygylic ester with styrene, which gives you a cyclopropanation reaction. What happens is the cationic gold causes a rearrangement of the propygylic ester to give you a gold carbene, and then that gold carbene cyclopropanates the styrene. And under these conditions, we were able to get a very high diastereoselectivity towards the cis diastereoisomer, which is fairly standard in these kind of reactions. We were also able to generate a 72 to 28 ER in the reaction. I'm going to focus on the major diastereoisomer as we go through this slide. What was also very nice, if we take the opposite enantiomer of our retaxane and we carry out the same reaction, we get the opposite enantiomeric ratio. And that's really important. So we're sure, or we have a reasonable certainty that the mechanical bond is providing the stereochemistry. It's not some adventitious chiral additive that somehow crept into our reaction and is influencing the outcome. And just for frame of reference, this is a reaction that was first developed in its enantioselective variant by Dean Toast back in 2005. And this is their optimized ligand for this transformation. And if you apply it in this reaction, what you find is you get an 84 to 16 ratio of your two enantiomers. And it's important to note that we are not beating the best catalyst for this reaction. And I don't think we were ever expecting to with our first example, but we're not so far off. We're in the ballpark of performance, even if we are not exceeding it. So I'm not going to talk about every single substrate in this slide. I just wanted to show you that we were able to extend this to other substrates. I wasn't just showing you a cherry-picked substrate that happened to be perfect. I'm going to highlight a couple of examples here, though. So this example here on the left-hand side with the pivloate ester, this was the one that we were hoping was going to improve our stereoselectivity, because that's what happened in the case of Dean Toast's paper. But unfortunately, what we find is that pivloate esters are really not tolerated very well by our catalyst, and we get a really low enantioselectivity. So that was a bad day in the lab for Andrew. The good day in the lab was if you take the benzoate ester and just make it more bulky, you can start to improve your enantioselectivities. And so we can get up to an 88 to 12 enantiomeric ratio, which corresponds to a 76% EE, which is not bad at all in the context of gold catalysis. So this is not a crystal structure. I want to make this very clear before I start talking about it. We did some molecular modeling to try and think about how the catalyst might be working. And so this is a model of the transition state for the key stereo differentiating step. So the bond that forms, which then determines the outcome of the reaction. As I say, it's a model. This is not the truth. This is just some representation to help us think about the problem. But when we did the modeling, what we find is we have lots of weak intercomponent interactions between our axial and our macrocycle, which are rigidifying the structure. And something I didn't highlight on the way through, which I have to do now, I do apologize, is that we add copper into our reaction to bind the bipyridine and the triazole. And so that's present in all of our reactions. It's an additive. The copper itself is not catalytically competent. We tested that. But what it does do is it prevents the bipyridine macrocycle from binding to the cationic gold and leading to basically a lewis basic inhibition. And what we also see in terms of intercomponent interactions is a pi copper contact, which appears to be rigidifying the system as well. And so these weak intercomponent interactions take what looks like might be a very flexible structure and seems to give it some kind of a more defined structure, which is then leading to the stereo differentiation that we see in terms of the outcome. And actually, we modeled both transition states for our diastereoisomeric outcome, so leading to the different enantiomers of our products. And we actually find that even with relatively simple modeling, we get a reasonable answer for the stereoselectivity of the reaction. So the modeling predicts the correct enantiomer, and it predicts a reasonable difference in energy barriers for that key stereo differentiating step. So I'm not in any way trying to say that this modeling is detailed enough to be drawing strong conclusions, but I guess what I'm trying to highlight is the kind of interactions which may be leading to our stereo differentiation, and also the fact that these molecules are tractable from a molecular modeling point of view with modern computational techniques. And we are now starting to look at that in more detail with a view to be able to predict the kind of structures which will lead to enhancements of enantioselectivity. So this, I do like summarizing several years of people's lives. Andrew Hurd did this work over about 2.5 years. I haven't talked about some of the more difficult parts. So separating the diastereoisomers of the in the initial step turned out to be incredibly challenging, and he worked very, very hard to overcome that problem. And I didn't really comment at the time, but the diastereoselectivity in that reaction is pretty poor, which made that problem even harder. But the ultimate success here is we've demonstrated for the first time that the mechanical bond can provide the stereochemistry in an antioselective reaction, this mechanical planar chiral stereogenic unit. So I've put a big tick next to mechanically planar chiral retaxane there. I'm not saying that all of the problems are solved by any stretch of the imagination, but we've definitely shown that you can make these molecules in a scalable fashion and that you can use them for something. I think that that's really, really important. But Fraser kind of commented that the mechanical bond opens up a lot of potential in stereochemistry, and I think you would probably think we were over-egging things if it was just mechanically planar chiral retaxanes. But actually, you can have topologically chiral catenanes, you can have axially chiral catenanes. There's a whole family of co-conformational stereogenic units where one interlock component desymmetrizes a prochiral stereogenic unit in the system. And then you have a whole host of other types of stereochemistry. And actually, as you increase the number of components in a mechanically interlocked molecule, you increase the opportunity for stereogenic units. And that the system is essentially infinite. You can keep getting new stereogenic units just by expanding the number of components. And so what I would say is, if you're interested in stereochemistry, if you're thinking about where you're going with your career, and you think you might want to do something a bit weird and interesting, I think there's basically a whole world of stereochemistry to explore within the mechanical bond. And just to kind of give you a little vignette, we can take our covalent auxiliary approach and we can apply it to topologically chiral catenanes. So this general idea of using covalent stereochemistry to direct the mechanical stereochemistry turns out to be quite general, and we published this at the start of 2019, and Florian, Jamie and Mature did a great job getting that over the line. So we're going to put a little tick next to topologically chiral catenanes there. And up until then, it's worth pointing out that topologically chiral catenanes had been separated by chiral HPLC, but there hadn't been a non-chiral HPLC synthesis of enantiopure systems where the only stereogenic unit came from the mechanical bond. But apart from that, the only tick I would add to this slide is this one on the middle left, which is the co-conformational point chiral system. All of these other stereogenic units are basically up for grabs. They haven't been made in an enantiopure form without some form of covalent stereochemistry being left in the structure. And actually, even then, it's pretty limited. I think Fraser's done some really nice work on the co-conformational helical chiral stereogenic unit, and there's some real potential there, especially with the dynamic systems, to do some interesting stuff. I just want to finish, and hopefully I'm not over time. I didn't actually put a timer on, which was a mistake. I kind of wanted to highlight other work in the field. I mentioned some on that last slide, but I think it's important to kind of say what the potential of these systems is. So Professor Takata, he of the 4% EE first stereoselective synthesis paper, has actually applied mechanical planar chiral stereogenic units in helical polymers and shown that the mechanical bond leads to basically selection of the helical chirality of the polymer. Hirose has generated mechanically planar chiral hosts, which selectively bind small chiral molecules and report on the hand of the molecule bound. Christoph Schalai and Baroncini and Creedy have generated chiral switches of different kinds using the mechanical bond. Fujita, I can't really describe this as anything other than a crazy catenary. Please go and read some of his stuff because the molecules he's making are quite mind-blowing. But he can get to some really complex stereochemistry in his systems with high selectivity, which is amazing. And then at the start of this year, Dave Lee published a really nice trick where he used a chiral leaving group to provide the mechanically interlocked product with no covalent stereochemistry in the system in 50% EE in a single step, which I think is a really nice feature and could be a really exciting new avenue for development. And a little plug for us at the end, if you're really interested in this stuff, we've written a review which kind of tried to capture the whole field up to 2018. Unfortunately, it has moved on since then. And just this year, we've published an article which focuses on strategies for how you make these molecules in an anti-pure form. And I think it's a useful read. I'm sure there's other stuff out there, but I think this is the first time that something's been published that focuses on the synthetic aspect. And I think hopefully there will be more to add to that in the near future. I'm aware of some really nice stuff that's coming down the line from other groups and from my own group. And so with that, I'd like to thank my group for all of their hard work and obviously the people who funded it. I've highlighted lots of people on the way. The people in red, whose names I haven't mentioned, are people who contributed to various projects that I kind of went through relatively quickly. But I think it's fair to say that everyone in my group has pushed really hard and achieved lots and lots, especially in the last couple of years. And I really appreciate all of their hard work. And with that, I'd like to thank the organisers for the invitation, Fraser for the incredibly kind introduction again, my group for their hard work, and the collaborators, some of whom are shown on the right-hand side of this slide. I'd be happy to take any questions.
Well, thank you very much, Steve. I think you have to maybe remove your presentation. Good. Okay, right. So I think you and I are going to have a little bit of a discussion because at the moment we're waiting, unless the chat has frozen on me, for some questions to come through. So while hopefully people are coming through with questions, and I'm going to stir the pot a little bit by quoting something that the late Ernest Elio said to me probably 25 years ago, which was, you know, Fraser, less than 5% of organic chemists actually understand stereochemistry. With that quip, I hope we'll get lots of questions coming through, and a few are coming. Good. So, but let me stay, since I get a chance to talk, with another story. Donald Cram once confided in me that when he was hiring postdocs, he went for people with good, as you called them, traditional synthetic backgrounds. I always remembered that, and I took that advice to heart, and there are many people that have come to my group with that kind of background, but I think this is something that, if you reflect on what you've been able to do, Steve, the so-called traditional synthetic background has been incredibly valuable. Would you like to comment?
Absolutely. I think synthetic chemistry allows you to make stuff, just as a very kind of general statement. And so if you enter any field with good synthetic skills, you can make contributions that maybe people who've come from, I'm thinking maybe a good specific example is in probes for biology. So most biologists use the same probe that they can buy. if you go into chemical biology with synthetic skills or recruit people with synthetic skills, you can start making probes that have different properties. And Natalie is actually doing some really nice stuff there. And I think that's one of the things she has at her disposal. She's come through the making of probes and development of probes. And if she starts moving into the applications of them, she has a massive leg up over people who just have to buy what they can buy. And so, yeah, I think synthetic skills will always be valuable, even if robots start doing a lot of our synthesis. I know that Carson's quite keen on this, Lee Cronin's quite keen on this. There's the synthetic skills to make things, and there's the synthetic skills to design things and plan things. I'm not sure that robots will be superseding us on those kind of higher level skills maybe anytime soon.
Well, I would tend to agree. I hope I don't upset Carson or Lee Cronin, but I think there's going to be room for the Steve Goldups. One interesting thing, people end up trying to search under your name. What I end up with, and I don't know if you do, Steve, from time to time, all the time, is you're not Goldup, you're Holdup.
Yep, I've been called that in the past by accident.
You have, right. Okay, I think we're getting some questions coming through. Steve, thanks for such a wonderful talk. This is from, again, Oleg Borodin. You've nicely demonstrated that mechanically chiral rotaxanes can successfully accomplish metal catalysis. What do you think about using mechanically planar rotaxanes for metal-free organocatalysis? This kind of catalysis might require a great diversity of functional groups to be present in a chiral pocket of the rotaxane.
That's a really good question, and I'd be lying if I said we weren't working on it. We've been playing with that idea for a while. And I guess, so the example you've given, this idea of multiple functional groups, that's probably one of the key values of the mechanical bond, because you can essentially display them in roughly the right orientation. And the analogy that people always make, and I want to be careful, but I think there is an analogy to be made here with the active site of an enzyme, where you have multiple functional groups displayed into exactly the right place to achieve the outcome you want. But of course, the field of artificial enzymes struggled a lot with the idea that if you make your system too rigid, you can essentially miss. So, your transition state doesn't quite fit, and so you have zero activity. The nice thing about mechanically bonded structures is they're relatively rigid, but they're flexible enough to kind of move during the catalysis or to flex for different substrates. And I think that's a key feature of enzymes to a certain extent as well. And so, yeah, absolutely, this kind of multifunctional catalysis is something we're very interested in. And of course, you could imagine mixing organocatalysis and metal catalysis in the same framework, and that could be a very, very neat trick, I think.
So I find it difficult to read the names because the print is very small, but we have one from Lucas, somebody or other. Steve, great talk. Just as, oh no, it's jumping all the time. Except the chiral catalyst, where else can you imagine interlocked chiral molecules to have benefits over the nowadays solutions technology?
So I kind of talked about a couple of them on the way through, and actually people have obviously done some of it as well. So Hirose has shown they can be used as sensors. So enantioselective sensing is still, I wouldn't say it was a solved problem by any stretch of the imagination. And what you would want to use that for is for detecting the hand of a chiral molecule without having to use chiral HPLC and to detect its enantiopurity. And that's actually a really big field in its own right. And there's some really nice stuff you can do both with just selective binding, but also using the stereodynamic nature of the mechanical bond to try and use that to express in some way the enantiopurity of your molecule. So that's something we're very keen on. And we're also interested in the idea of using the mechanical bond for optical properties, so generating systems that emit CPL and things like that. So those are two areas that I can say that we're interested. I have to say one of the big things about doing this kind of work is you want to throw tools out there and you want other people to pick them up and use them. So I can't pretend that I'm the only, I'm going to come up with every possible application of mechanically chiral molecules. We want other people to get involved, and I think that's a really important part of science.
Okay, here is another very short question from Milo. Thank you for an interesting talk. Have you considered synthesis of chiral polyrotaxanes?
We've considered, and we might be doing something on it. I kind of feel as though I shouldn't give too much away here, but yeah, we are looking at whether we can make oligomeric structures with control of their stereochemistry. And if you think about mechanical planar chirality, we can assign a configuration to each of the macrocycles on the axle. And so you can imagine you can write stereochemical information with different macrocycles on the way down. And that's essentially still an unsolved problem. Fritz Wertler did make these kind of mechanically planar chiral 3-rotaxanes and separated them by chiral HPLC, but making higher order systems isn't a solved problem at all.
Another short one, Steve, how the configuration of your chiral MIMS how can they be determined when an X-ray structure is not available?
Oh, so this is a lovely question because it lets me plug a paper I forgot to mention on the way through. We published an article with Brunjan from the Netherlands at the start of this year using vibrational circular dichroism. So by modeling the structures and basically generating a computed VCD spectrum and comparing them to the experimental VCD, we got really good agreement. And so the ultimate idea would be able to assign the stereochemistry using spectroscopic techniques when you can't get an X-ray, because that is a real problem. We have papers where we haven't been able to get X-rays and they get held up for a while because you really want to know the stereochemistry of your molecule. And actually, you need to know the stereochemistry, say, of your catalyst, because if you don't, it's really hard to make rational changes. You want to be able to know the mechanical configuration, which leads to one of your enantiomers of your product, to be able to do some molecular modeling so you can validate how that's happening, and then you can optimize your catalyst. And so it's a really key challenge.
Right, Steve, the last question I'm going to take from the list here is from Yavid. Very impressive talk. While using as catalysts, can we think of using molecules for bimetallic catalysis, where two metal centers are present with different redox potentials?
Absolutely. And again, this goes back to maybe a benefit of the mechanical bond. You could imagine burying one of the metal centers within the cavity. So I showed you in our gold complex is actually formally bimetallic. We have a copper center bound in the cavity and we have the gold hanging off. The copper is passive, it's not part of the catalytic cycle. But you could imagine having one catalytic metal in the cavity, one dangling off, and you can say prevent what you might call incompatibilities between the two catalysts because one is sterically confined. And that has some potential, I think.
All right, Steve. So I think we're running out of time, but I want to be a little bit selfish and take the last minute or so to ask something that is fairly fundamental. We see a trend towards this whole concept of nano-confinement. And in order to get there, molecules are probably going to have to grow in size. I've spent quite a bit of time reading all about David Lee's nice work on molecular knots, trifoil knots, pentafoil knots, and even more exotic knots. And as they get bigger and better and more impressive, and of course, built in there is chirality. And you have everything that you really need. You have the chirality, you have the possibility of nano-confinement, you have the ability probably to be able to introduce all kinds of functional groups to aid and abet metal catalysis and so on and so forth. So this whole business of nano confinement that has been pushed a lot by Raphael Klein of late in a major review in Nature Nanotechnology. And finally, a little plug for my own little viewpoint article in Nano Letters based on David and Ali Trabolsi's contributions to the molecular knot field in the last decade. Chemical topology, and my co-laureate Jean-Pierre Sauvage is on the same wavelength as I am here, is going to be enormously important. And I've taken the courageous step of renaming it so that it gets more consideration, nanotopology. So there's quite a few comments there. To summarize, what about knots? What about nanotopology? And what about nano confinement for the future?
Okay, so taking knots first, I'll do them in order so I can keep them in my head. So the knots are really, really cool. I completely agree. And they have some of the properties of interlocked molecules, and they have some properties which they're less flexible a lot of the time. But they do, that is a benefit, I think, especially when you're trying to express the stereochemistry. And they express really complicated stereochemistry. I think it's really, really beautiful stuff. And the key challenge there is to make them enantiomer pure. And there are some nice examples of that in the lower order knots, so in the trefoil knots. And there's some nice stuff coming down the line, I think, in terms of the higher order knots. So yeah, absolutely. And they do create large objects very quickly. So some of even though they're the smallest knots ever made, they're still big on molecule scales. And so you are starting to think in the nano region, absolutely. So you have these kind of nano, basically surfaces, which are textured by the overlapping chains, and that creates a really interesting potential when you think about using them in nano confinement. I completely agree. What those applications will be is always going to be interesting, right? We think in terms of catalysis maybe, or we think about binding of proteins, for instance. You could imagine the knots have quite an unusual surface, and you could imagine those binding to the surface of a protein. Obviously, both a knot and a protein have basically shape to them and stereochemistry to them, and so that could be a very, very selective process indeed. So I think I've rambled a bit, but hopefully I've touched on at least some of the points you were interested in. And yeah, I think generally this idea of nano confinement, this really comes down to becoming even more detailed about our understanding of what's happening at the molecular scale. The interaction between large objects and small objects, or two large objects at the molecular level of detail. And it's really exciting that we're getting to that now. You know, we saw a really beautiful cryo-EM structure the other day at the atomic, with atomic level resolution. And you could start thinking about how you would visualize these knots interacting, say, with proteins and actually knowing how they're fitting together. I think that could be really beautiful stuff.
Well, thank you, Steve, for winding up on these kind of dream situations that are ahead of us. I just want to wind up by saying I've been immensely privileged this afternoon to listen to 3 stellar talks by the people who are leading, in my opinion, the field. Wouldn't necessarily call it supramolecular chemistry. I would call it contemporary chemistry. I would call it chemistry of our time, chemistry of our age. And I not only want to thank Natalie and Carson and Steve, but also to thank Kira for organizing this meeting, along with all other supporters from Wiley. I think they've done a marvelous job, and in these difficult times, it keeps our inspiration levels high, and our knowledge levels also on par with our inspiration to be able to hear what the brightest and best of the new generation of contemporary chemists are doing. So thank you all, and over to you, Kira.
Thank you, Fraser, for this excellent moderation, and to the three speakers for the great talks. Ruben, thank you as well for the technical support. That was our second virtual symposium. I hope you enjoyed it. There are more events coming up soon, not only from ChemPhysChem, but also from our sister journals. I will share the screen with you for a second. The next one is being organized by our sister journal, Chemistry Open. Can you see the screen?
Yeah.
Can you see it? It's being organized by Chemistry Open. It will take place on November 17th at 6 p.m. CET on open source research and open data. It will be moderated by Marcus Hanwell and include presentations by Matthew Todd, Romy Amaro, and Alberto Pepe. It would be great to see many of you there. Well, that's it for today. Thanks again for joining us, and see you soon. Bye.